again, and welcome back again to my messy basement. As I promised, I want to make another video taking a look at the learning outcomes that I posted for the course. So this is that summary document that describes all the learning outcomes that we've got. But this time I've got highlighted what learning outcomes are going to be on the final exam. So let's take a look. So this is a document that I published twice now. This second time that I published it, I've highlighted the learning outcomes that are going to be assessed on the final exam. I haven't finished typesetting the final exam yet, but I've created all the questions, and what I've done from that set of questions is these are the learning outcomes that guided the questions that I created for that. So that's what you're going to see highlighted here. So as I said, this is it's meant to be a cumulative exam. So there are some things that are going to be on the final exam from the first half of the course, but you've been assessed a lot on some of the things from the first half of the course. So there's not really much reason for me to reassess you on those things. The first thing that you're going to be reassessed on in this final exam is this learning outcome here from week 2. This is going back to threads. I've highlighted this as final sort of, and the learning outcome is identify the critical sections requiring mutually exclusive access in a piece of code that will be run concurrently using threads or processes. This is something that I've included in a question where I'm not actually going to show you any code, and that's why this is a sort of. It's more of I'm going to describe code to you, and I'm expecting you to know what the operations are that the code would be doing. So this is in relation to something else that's later in the course. I'm expecting you to know approximately what operations the code that's not shown to you could be doing, and then thinking about how that could be a critical section and trying to think about how concurrent execution of those operations, so again, not really code so much as operations, how concurrent execution of those operations could lead to a critical section. So in this case, you're not going to be seeing any code, but you do have to think about how running code concurrently that implements certain operations could lead to having a critical section in some code. The other ones that you're going to be assessed on are from week 3 on scheduling, and the things that I'm looking at here are compare and contrast different scheduling policies and describe a scheduling algorithm used by a modern operating system. So for these two, I'm really specifically thinking about the set of scheduling policies that were in the first part. So the basic ones, first in, first out, FIFO, shortest job first, shortest time to completion first, round robin, and multi-level feedback queue. I'm not thinking about the completely fair scheduler. I'm not thinking about lottery scheduling. I'm not thinking about anything from the Linux kernel. So when I'm thinking about this, I am really not going to ask you the same question that I asked you on the term test. I'm not going to ask you to apply scheduling policies to a workload. I'm going to be asking you more about comparing and contrasting the behavior of these scheduling policies with different settings. So making comparisons between the scheduling policies with different settings. In the first version of this document that I posted, I just deleted this part 2 from week 3. I've stricken it here because you have actually been assessed implicitly on one of these. In assignment 3 for the EXFAT file system, you don't really have to describe the physical structure of a hard drive, but you do have to be able to think in terms of things like sectors and stuff to be able to do the assignment at all. So you've been assessed on that partially, but the rest of it you don't have to worry about. You're not going to be assessed on that. Starting in week 4, though, these are pretty much all of the learning outcomes that you can expect to see on the final exam. So I'm going to start at the top here. Describe the data structures used to represent files and directories as seen in Unix. So you are not formally assessed on this in assignment 3, but again, you're kind of informally assessed on this in that you have to recreate a tree structure to represent folders and directories. The data structures here that I'm thinking about are inodes. So specifically in Unix, to describe the data structures are inodes. They're inodes. The relationship between inodes and files and directories, the kinds of metadata that are kept in inodes, and how inodes are referring to data in the data region. Some of the other stuff that's a data structure are things like allocation structures, so bitmaps, the inode bitmap and the data bitmap. And the other thing is just like high level stuff, so like the superblock and a file system, and then just the different regions, so the inode table and the data region. You should also be able to, at this point, be able to describe these ideas in terms of exFAT. And exFAT isn't really a Unix file system, it's a Microsoft file system. It's a Microsoft file system, but you should be able to describe things like the main boot sector. No, you don't have to describe in detail like how many bytes each of these things are, but you should have a general sense of the main boot sector is effectively the same thing as the superblock in an in a VSFS or ext2 file system. Directory entries correspond to inodes sort of in an exFAT file system compared to VSFS. Show how common file operations are performed in terms of manipulating a file system's data structures. So we talked a little bit about this in class in terms of here's a small code segment. Here are some calls to open, read, and write, and close. How do those file operations make changes to the file system's data structures? So how does, for example, the write system call make changes to an inode and the data blocks and the data bitmap in a VSFS file system? How does the write system call make changes to the data structures in exFAT? So how does it add new directory entries for a file? How does it allocate things in the heap? Does it have to change the FAT? Does it have to add entries to, add entries to the allocation bitmap? Does it have to change the allocation bitmap itself if we go past the size of a cluster? You are not going to be assessed on this in the final exam. So explain how files are managed as part of a process's active state. You were assessed on this in the term test in the form of asking questions about the open file table in a process. So this was going back to things like talking about pipes and stuff. So when the pipe system call is made, it's making changes to the open file table. You're not going to be assessed on that in the final exam. Describe how a specific file system is implemented. This is related to show how common file operations are performed in terms of manipulating a file system's data structures, and it's related to describe the data structures used to represent files and directories. Describe how a specific file system is implemented. You should be able to describe both VSFS, ext2, so that's one file system, and you should be able to describe how exFAT is implemented. So high-level data structures, approximate location of where things are, the order of operations in terms of the order of operations, or less specifically and more generally, what data structures are modified when something happens, so when we're making changes to a file. You're not going to be assessed on write code to read file system. I'm not asking you to write C code here to read VSFS or exFAT. That has been adequately assessed on assignment 3. That has been adequately assessed on lab 3. Moving on to, this is file system consistency and redundancy. So this part of this week was talking about file system checking, FSCK or fisking, and journaling and RAID. So all three of these things. Choose an appropriate RAID level given requirements, and compare and contrast different RAID levels. So these two learning outcomes are nested like this because they are related to each other. In class, this was an exercise that we did where here is a workload. Here's a description of what somebody wants or needs. Tell me what RAID level you would pick for this person and why you would pick that RAID level for this person or for this workload. I would want you to be able to, here's a situation, here's a set of requirements, tell me why you're picking a RAID level, and tell me why you're not picking the other RAID levels. So choose one, this is why I should think that this one is important, given these different performance requirements for RAID levels or for RAID, and this is why I'm not picking these other ones. Describe what a human operator might see in files when a file system is in an inconsistent state. So this is, we did this in a Kahoot, and the idea here is a set of inconsistent file systems. It's inconsistent in this specific way. What does it look like when I open up my file explorer? Identify inconsistencies in a file system and repair inconsistent file systems. You weren't really repairing an inconsistent file system in Lab 3, but I'm just going to say that we kind of could have done that. We could have gone to that point of this value should be changed to this. Identify inconsistencies in a file system. You definitely did that in Lab 3. That was going through the process of making sure that the MBR, the main boot sector, was consistent with the allocation bitmap. I'm not going to ask you to identify inconsistencies in a file system. You may need to describe inconsistencies, but I'm not going to be like, here is an example file system. Tell me what the inconsistency is in this file system. So you should know how a file system can be inconsistent. Again, high-level data structures. You should know how it can be inconsistent, especially related to this, but you're not going to be given a file system and asked to identify that inconsistency. Describe strategies for repairing or preventing inconsistent file systems. Here, I'm looking for you to describe the ideas of file system checking, journaling, and that's it. That's it. Those are the only two that are for preventing or repairing inconsistent file systems. RAID does not know anything about file systems, so RAID has nothing to do with repairing or preventing inconsistent file systems. This is purely file system checking and journaling. Compare and contrast strategies for repairing or preventing inconsistent file systems. So I'm not going to ask you to compare and contrast these. This learning outcome you will not be assessed on at all this term. I'm not looking for you to make comparisons between file system checking and journaling. Compare and contrast traditional file systems with modern approaches such as log structured and, which log structured and has been crossed out, journaling file systems. Journaling file systems is the one that we're focusing on here. A file system like exFAT does not have a journal, and a file system like ext3, which was the next, the successor to ext2, which is effectively what we're looking at with VSFS, does have a journaling. What does adding the journal actually give you? What do you get out of that? What's slower about it? And then kind of what I'm thinking of is, what specific kinds of things can journaling solve? So how does journaling help us? What is journaling actually trying to accomplish? And thinking about things like how journaling effectively turns things into atomic operations, sort of. In week 5, I've tried to cut out the duplicate, so the beginning and continuing learning outcomes in week 5 and 6, and that kind of reduces the amount of learning outcomes here. But weeks 5 and 6 were entirely about virtual memory and different implementations of virtual memory. So in the beginning of virtual memory, we're talking about base and bounds, and I'm looking for you to be able to explain how a process's entire address space can be provided or supported via the concept of virtual memory. So this one is kind of like telling me about, you know, we've got a virtual address space that may be bigger than physical memory. All these other learning outcomes below it tell us how we can put this entire address space into physical memory, into a physical memory that's maybe smaller than it. So base and bounds, segmentation, and paging, linear page tables. Translate virtual addresses into physical addresses. I'm expecting you to be able to do this for all 3 of segmentation, base and bounds, and linear page tables. Not for page directories or multi-level page tables, but linear page tables, yes. With segmentation, I'm expecting you to be able to do this with the explicit approach, not the implicit approach. So I'm not going to be asking you about Here's, this address came from the program counter. Tell me which segment it goes into. It's more of a, here's an address, given explicit segmentation. How do you translate this into a physical address? With memory segmentation, discuss the benefits of partitioning memory and address spaces. I never used this word in class, partitioning. I used the significantly less formal, breaking it up into fixed size chunks, but that's what partitioning is. Partitioning is taking something that's bigger and making it into smaller pieces. Partitioning memory and address spaces with segmentation, we are partitioning virtual address space. With base and bounds, we're partitioning physical memory. With paging, we are partitioning both physical and virtual memory. Describe what happens in various parts of the system when a segmentation fault happens. So this is what it says on the box. I'm expecting you to be able to tell me about what your program is doing. I'm expecting you to be able to tell me about what the operating system had to do when it started and what it's doing when the segmentation fault happens. I'm expecting you to tell me what the shell is doing, what your shell program is doing. And I'm expecting you to tell me about what the hardware is doing for each of these different I'm expecting you to tell me what the hardware is doing when a segmentation fault happens. So for each of those different parts, I'm expecting you to tell me what they're doing when segmentation fault happens. Compare and contrast free space management policies. So here I'm looking for you to apply free space management policies. That's a little bit lower on the Bloom's taxonomy than compare and contrast. I'm expecting you to be able to apply them and then tell me about the outcome. So like, how does this free space management policy, so first fit, next fit, best fit, worst fit, how does this compare to another one, given the layout that we've just arrived at, or given the pattern of allocation that we've just arrived at? So does this lead to a more spread out set of allocations? Is everything pushed up to the top? Yeah, that's what I'm expecting you to be able to do for something like that. And the last set of learning outcomes here, describe how the operating system works with the underlying hardware to manage paging and virtual memory. So when the operating system starts up, it has to set up that fault handler. And then this is telling the hardware like, hey, if there's a fault, you should call me here. Call me here so I can run this code. And then once that fault happens, the operating system has to handle the fault. The hardware tells the OS a fault has happened. It's the OS's job to handle the fault. The operating system has responsibilities for each of those three different approaches to virtual memory. So paging, segmentation, base and bounds. It has to keep track of different things in the process control block. And then it has to set values in hardware when context switches happen. So it has to set the base and bounds register, or it has to set segment registers, or it has to set the page table base register. Explain the operating system data structures and algorithms used to manage a partitioning strategy, such as paging. In this one, what we're talking about is the linear page table. So what kind of data structures are there to be used for implementing a page table? And this kind of looks like a page table. That's kind of what I'm looking for you to be able to tell me. I'm not going to be asking you questions that are detailed about what are the very specific things that are in a page table entry. I'm not printing out the Intel documentation for you. I'm looking generally for what kinds of things are in a page table entry, and what does a page table look like? Compare and contrast the solution of multi-level page tables with file system implementations. This is one of the last things that we did, and I'm really looking for you to just give me some examples of how page tables, multi-level page tables, this is page directories now, and file system implementations are similar to each other. The file system that I'm really thinking about here is VSFS. It's not really similar to EXFAT. It's not really similar to EXFAT. It's a lot more similar to the way that VSFS and EXT work. So that's what I'm looking for there. And then finally, compare and contrast methods for address translation. So with all three approaches to address translation, segmentation, base and bounds, and paging, you should be able to tell me about, this is generally what it is. this is what's bad about it, this is what's good about it, and then based on what's bad about it, this is why we moved up to the next one. So why did we go from base and bounds to segmentation? Why did we go from segmentation to paging? And that's it. That's the end of this document. All right, so I hope that that gives you a good sense of what to think about in terms of preparing for the final exam. I wish you the best of luck. I'll say that again on Tuesday when I see you in the morning. And yeah, I hope that you otherwise have a great weekend. Bye.